If VLAN and switching questions keep tripping you up on the CCNA, you're not alone. A lot of people memorize commands, but never really build the picture of why flat networks break down in the real world. In this lesson, we're going to fix that. You'll see how switching, VLANs, trunking, inter-VLAN routing, and spanning tree all connect, not as random exam topics, but as one system that makes modern networks actually work. We're going to connect the theory to what a switch is actually doing, so questions about forwarding, segmentation, and layer 2 design stop feeling abstract. By the end, you should be able to look at these CCNA topics and decode them with a lot more confidence. Think back to early Ethernet with hubs. Every device was sharing the same collision domain, which meant the whole network was basically taking turns. If two hosts tried to transmit at the same time, they stepped on each other, and only one transmission could actually get through. So the network had to run in half duplex. A device could send or receive, but not both at once, and it relied on CSMA-CD, meaning devices had to listen first, detect a collision if one happened, then back off and try again later. Bridges were the first big improvement because they broke up collision domains instead of leaving every device stuck in one shared mess. A switch takes that same idea and scales it way up. In practical terms, a modern switch is basically a high-speed multi-port bridge doing that job on every single interface. And because each active switch port can run full duplex, a host can send and receive at the same time. That's the key shift. On that link, collisions are gone. Here's the core idea behind MAC learning. When a frame comes into a switch port, the switch looks at the source MAC address and learns this address lives on this interface. It then stores that mapping in the MAC address table. Now, if the switch doesn't know the destination yet, or the frame is a broadcast, or an unknown multicast, it has to flood it. That means it sends the frame out every other port in that same VLAN, except the port it came in on. Once the switch knows the destination MAC address, it can send the frame only out the correct port. If the traffic would stay on the same interface it arrived on, the switch filters it instead of sending it back out. And if an entry sits around too long without being used, it eventually ages out of the table. Here's the exam shortcut I want you to remember. On a switch, each port is its own collision domain, because every link is being switched separately. That's one of those small facts that answers a lot of CCNA questions fast. Broadcast domains are a different story. A broadcast stays inside its VLAN. It doesn't just spill everywhere in the switch network. If that traffic is going to cross a VLAN boundary, you need a layer 3 device to route it. If you want a clean exam shortcut, use this one. Count one broadcast domain per VLAN and one collision domain per active switch port. Keep that rule in your head, and a lot of those CCNA questions get much easier. This is where VLANs start to matter. A VLAN lets you take one physical switch and split it into multiple logical networks. So even though the hardware is shared, the devices behave as if they're sitting on separate switches. The benefit is that you cut down unnecessary broadcasts inside each group, and you stop traffic from one department from automatically spilling into another. In other words, VLANs improve segmentation and usually improve performance too. Picture one switch serving both finance and engineering. Without VLANs, they're sharing the same broadcast space. With VLANs, you can separate them logically even though they're plugged into the same hardware. That gives you cleaner performance and better security boundaries at the same time. And that's exactly why VLANs show up so often on the CCNA. They define your broadcast boundaries, and the moment you separate users into different VLANs, you've also created the need for inter-VLAN routing if those groups need to communicate. Here's a classic CCNA trap, and it's one a lot of people miss. VLANs can persist even when you think you've cleared the switch, because on many Cisco switches, the VLAN information is stored in VLAN.dat, not inside the startup configuration. So this is the warning. Erasing the startup configuration does not automatically remove your VLANs. If VLAN.dat is still there, that VLAN database can come right back after a reload. That's exactly the kind of detail that catches people on the exam. Also remember, some VLANs already exist by default. And if you're dealing with VTP, a bad revision number from another switch can overwrite the VLAN information you expected to keep. That's one of those details that can turn into a real mess fast. An access port carries traffic for one VLAN. That's the port type you usually use for an end device like a PC, a printer, or an IP phone. A trunk port is different. Instead of carrying traffic for just one VLAN, it carries traffic for multiple VLANs at the same time. That's what you use between switches, or between a switch and a router or layer 3 switch. So here's the contrast to lock in. On an access link, the frame is sent untagged for that one local VLAN. On an 800 2.1q trunk, the frame carries VLAN information with it, so multiple VLANs can share the same link. On an 802.1q trunk, the switch inserts a 4-byte tag into the Ethernet frame. You can picture that tag as a label riding with the frame, telling the receiving device which VLAN that traffic belongs to. Inside that tag, you'll see fields like TPID, PCP, DEI, and the VLAN identifier itself. For the exam, the big thing to remember is that the normal usable VLAN ID range people usually talk about is 1 through 4094. The native VLAN is the big exception, because native VLAN traffic is sent untagged by default. And this is where the warning comes in. If the native VLAN doesn't match on both ends of the trunk, you can create some really messy connectivity issues, and even security problems. When you're troubleshooting this, think like an operator. First, verify that the link is actually trunking. Next, verify which VLANs are allowed across it. Then make sure both sides agree on the native VLAN. That's the practical checklist. When you configure this, you usually start by creating the VLANs and giving them clear names. That way the logical networks exist on the switch before you start assigning ports to them. Next, take the user-facing interfaces, put them into access mode, and assign each one to the correct VLAN for that department or device group. That's how you place the endpoint into the network you actually want it to live in. Then configure the uplink as a trunk and allow only the VLANs you actually need. And as a best practice, use an unused native VLAN like 99 instead of just leaving the default in place. When the exam gives you a partial config, treat it like a troubleshooting scenario. Ask yourself, does the VLAN even exist? Are the access ports assigned correctly? And do the trunk settings actually carry that VLAN all the way across the path? Verification is where you catch mistakes quickly. One of the most useful commands here is show interfaces trunk. It tells you which ports are trunking, which VLANs are allowed, and which VLANs are actually active on that trunk. Show VLAN brief is another quick check. It helps you confirm that the VLAN exists and that the access ports you expect are actually assigned to it. Then check Show MAC address table to see whether the switch is learning devices where you expect it to. If a VLAN is missing or a port is in the wrong mode, the MAC table often gives you the clue. The moment devices sit in different VLANs, they're also sitting in different IP subnets. And that's the handoff point to inter-VLAN routing, if those devices need to talk to each other. A layer 3 device has to move that traffic between them. The oldest way to do this is pretty literal. You use one physical router interface per VLAN. It works, but you can probably see the problem right away. As the number of VLANs grows, that design gets clunky and doesn't scale well. Router on a stick improves things by using one trunk link with multiple sub-interfaces instead of a separate physical interface for every VLAN. But in modern networks, a layer 3 switch using SVIs is usually the cleaner and more scalable best practice design. For the exam, don't just memorize the names of these designs. Know when each one shows up and why. If the question is really about scalability, the better answer is usually the layer 3 switch doing the routing with SVIs. In router on a stick, you have one physical router interface connected to the switch as a trunk. Then on that single router port, you create a separate sub-interface for each VLAN. So one link is carrying traffic for multiple VLANs, and the router separates them logically. On each sub-interface, first configure encapsulation.1q with the correct VLAN number. Then assign the IP address that hosts in that VLAN will use as their default gateway. That order matters, and it's worth being deliberate about it. This is one of those command order traps the exam loves. If encapsulation.1q is not set correctly on the sub-interface, the rest of the addressing and routing logic won't map traffic to the right VLAN. So don't just memorize the commands, notice the dependency. Also check the switch side like a troubleshooter would. Make sure that link is actually trunking. Router on a stick breaks immediately if the uplink is left as an access port or if the VLAN isn't allowed across the trunk. On a layer 3 switch, the approach is cleaner. You create an interface VLAN or SVI for each subnet, assign it an IP address, and enable IP routing so the switch can route between VLANs on its own. At that point, the SVI becomes the default gateway for hosts in that VLAN. And that's why this scales so much better. You're not forcing every routed hop out to some external router. The switch is handling that routing locally. Here's another exam trap you absolutely want to catch. An SVI can stay down even when the configuration looks correct, simply because there isn't an active access port up in that VLAN. So if the SVI is down, don't assume the IP settings are the problem first. So if an SVI won't come up, run a quick checklist. Verify that the VLAN exists, verify the interface isn't shut down, and verify that at least one live port in that VLAN is actually up. Those are the big 3. Redundant layer 2 links are great for resilience, but they come with a serious risk. Without spanning tree, those extra paths can create switching loops, and once that loop starts, it doesn't just fade away on its own. And when that happens, the symptoms get ugly fast. You can get broadcast storms, duplicate frame delivery, and MAC address table instability, because the switch keeps relearning the same source MAC on different ports over and over. Classic STP fixes the loop problem by blocking redundant paths. RSTP does the same job, but the important difference is speed. When the topology changes, RSTP converges much faster. On Cisco networks, PVST Plus runs a separate spanning tree instance for each VLAN. So VLAN 10 and VLAN 20 can make different spanning tree decisions, even on the same physical links. For example, VLAN 10 might elect switch A as the root bridge and block one uplink, while VLAN 20 elects switch B and blocks a different port. Spanning tree starts by electing a root bridge. The winner is the switch with the lowest bridge ID, and that bridge ID is built from the switch priority plus the MAC address. So priority matters first, and the MAC becomes the tiebreaker. From there, each non-root switch chooses one root port. That's its best path back to the root bridge. Then on each network segment, spanning tree chooses one designated port, which is the port allowed to forward traffic for that segment. Any ports that aren't selected for forwarding get blocked, and that's how spanning tree breaks the loop. In real networks, you usually don't leave root election to chance. You tune the priority so the switch you want, usually the core, becomes root on purpose. And when you verify spanning tree, show spanning tree is the command to reach for. It lets you confirm who the root is, what the port roles are, and whether the topology actually matches the design you intended. If you can hold on to the big ideas from this lesson, you're going to be in really strong shape for the exam. Think switch forwarding logic, collision domains versus broadcast domains, access versus trunk behavior, VLAN.dat persistence, router on a stick command order, SVI conditions, and the main STP roles. That's a lot of the real payoff right there. That's the switching foundation you really want in place. In the next lesson, we'll build on it by moving into OSPF, where routing decisions take over once traffic leaves the layer 2 world. So if this clicked for you, the next step is going to make a lot more sense.